Greetings. I hope you're ready to take some notes. Grab your math notebook and your favorite pens. I'm partial to these ones. And let's call it polynomial functions. The brand new function family that we are learning in Math 3. You already know some polynomial functions. You know linear functions, those are degree 1, and those classify as polynomials. And you know quadratic functions, degree 2, those also classify as polynomials. The word poly, the root poly, means many. Someone who is polygamous has many spouses, for example. Can you think of another word that has poly in it that means many somethings? And then the word nomial refers to a name or a term. So polynomial functions are functions that go by many names and contain many terms. And the first thing we're going to write down is, how do we name them? Naming them. When we are naming and describing polynomial functions, we actually use two names, a first name and a last name, where the first name refers to what degree it is, and the last name refers to how many terms it has. We name polynomials based on their degree. And when we say degree, we're referring to the highest exponent and the number of terms. We name polynomials based on their degree and number of terms when written in standard form. And they're not always going to be written in standard form, as you saw on Monday's quadratics review. Sometimes you have to take the factors and multiply them together and put it into standard form. Then you count the terms, and that will be the last name. Okay, so if we're naming based on degree, I'm going to underline the word degree here, and we're going to call this the first name. Based on degree. So let's make a little table where we can write degree, name, example. Okay, so let's start with a degree 0 function. What does that even mean? Well, it's called a constant function. An example would be something like y equals 3. It is just a horizontal line. It's constant. It has no slope. It's like y equals 0x plus 3. We don't write the 0x, but this is a function that never crosses the x-axis. It's constant, no slope. And you might be wondering, why is it considered to be degree 0? I don't see any highest exponent of 0. But could we write this as y equals 3x to the 0 power? Is that the same thing as y equals 3? Well, what is x to the 0 power? Anything to the 0 power is just 1, and 3 times 1 is just 3. So there's no need to write the x to the 0, but it's there, it's invisible. You can throw an x to the 0 on any term, any constant term, like just a number, and it wouldn't change it. It would just be excessive. Once we move up a degree, once you have a degree 1 polynomial, we call that linear. You know about these. It's like our y equals mx plus b. Y equals 1/2 x plus 1 is an example of a linear function. It's considered a polynomial. You might be wondering where you see this degree 1, and it's invisible also. It's the exponent that we could write on the x variable. It's 1/2 x to the first plus 1, but x to the first is just x. No need to put the 1 exponent there. But that's what makes this a degree 1. I don't see any exponents higher than the invisible 1 on the x term. As soon as we move up to degree 2, we have a new name. You know it. We learned it in Math 2. Quadratic. Is it a coincidence that we learned degree 1 linear polynomials in Math 1 and degree 2 quadratic polynomials in Math 2? And we're about to learn degree 3 cubic polynomials in Math 3. Spooky. So an example of a quadratic function would be something like x squared plus 2x minus 3. That's written in standard form. Its highest degree is 2, because 2 is the biggest exponent, so it's quadratic. Degree 3 polynomials we call cubic because a cube is 3-dimensional. Something like y equals x cubed minus 2 would be a cubic function, shifted down 2 units. Degree 4, what if the highest exponent is a 4? That's called quartic. Y equals x to the 4th plus 3x squared minus 10. Why not? And if it's degree 5, that's called quintic. Or is it quintic? 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 I don't know. That's when the highest degree you see is 5, x to the 5th power. I'm just going to make up a random polynomial function. It has a quintic term, a cubic term, a quadratic term, and a constant term. Altogether, we're going to name it based on its highest exponent, which is a 5. Degree 5 is a quintic polynomial. And I think we're just going to go up one more. Degree 6. If the highest exponent on the x variable is a 6, that is called sextic. Or sometimes hexic. You can choose which word you prefer. Sextic or hexic are interchangeable. They both refer to polynomials whose highest exponent is 6. X to the 6th minus 4x plus 3 is an example of a sextic polynomial. That's just the first name. So any of these words in this column you will use by identifying what degree it is, what's the highest exponent, and then call it by that first name. The last name, on the other hand, refers not to the degree, but the number of terms that polynomial has. So for the last name, we're going to write a number of terms, name, example. If there is only one term, like in this first example, y equals 3, one term. We can't have 0 terms. I'm not going to start at 0 because it would just not be there. If there were 0 terms, it would be invisible, and it wouldn't even be a polynomial. But if there is one term, we call that a monomial. An example of a monomial would be like 4x cubed. There's only one term. This over here is a constant monomial because there's only one term and it is degree 0. As soon as there are 2 terms, like in my linear example, there's 2 terms, we call that a binomial. It's a subset of polynomials, but instead of poly, many terms, there's exactly 2, so it's binomial. An example of a binomial might be something like x to the 4th plus 17. There are 1, 2 terms. Terms are like the chunks separated by plus or minus signs. As soon as you have 3 terms, can you guess it? A bicycle has 2 wheels and a tricycle has 3 wheels. This is called a trinomial when it is a polynomial with 3 terms. There's an example of a trinomial over here, 1, 2, 3 terms. They are not like terms because they all have different degrees, so they cannot be combined. Let's write a different example of a trinomial. X to the 5th minus 4x to the 2nd plus 1. There are 3 terms, a quintic term, a quadratic term, and a constant term. The 3 chunks are separated by plus or minus signs, so we're calling it a trinomial. And if it's 4 or more, that's kind of where the common names end. Boring. We just call it a polynomial after that. So if there's 4 or more terms, it's just a polynomial. I think there are probably names for it, but that's going to get into some obscure territory. So there's an example of a polynomial over here. Maybe it's x to the 6th plus 3x to the 5th minus 2x squared plus x minus 2, 3, whatever. This now has 1, 2, 3, 4, 5 terms in it. So we call that a polynomial. Anything more than 4 terms? Polynomial. So let's look at a few examples. I'm going to write 3 polynomials down, and you can pause the video if you want and name them. Give them a first name and a last name based on their degree and their number of terms. Okay, example 1, x to the 4th minus 3x squared plus 17. Figure out what is the highest exponent, what degree is it, that's its first name. Figure out how many terms it has, that's its last name. Write it down right next to the function. Function 2, or polynomial 2, x cubed minus 1. And finally, third example, 2x squared plus 1/4 x to the 6th minus 2x plus 1. Okay, if you need to, pause the video. All right, this first one here has a first name, quartic, because it is a degree 4. And its last name is 1, 2, 3, trinomial, because it has 1, 2, 3 terms. This second function, x cubed minus 1, has a highest degree of 3, so it is cubic. And because there's only 2 terms, 1, 2, it's a binomial. And number 3, a little tricky. People are sometimes tempted just to look at the first term and grab its degree and call this, in this case, quadratic. But this is not quadratic because 2 is not the highest exponent. It's a little scrambled. Conventionally, we would write the highest exponents first, and the different terms would be in descending order from greatest to least. But in this one, it's a little mixed up, and the second term actually has a higher degree than the first term. The highest degree is 6, so this is a sextic or a hexic. Okay. And because there's 1, 2, 3, 4 terms here, 4 or more terms, we just call it a polynomial. Degree 6 or sextic polynomial. How did you do? On this next page, we're going to make another table where we have degree. And let's just shoot that all the way down to the bottom of the page. Example. And then our last column is number and nature of roots. Roots are one of the most important concepts when dealing with polynomials. Roots are sometimes thought of as x-intercepts, but sometimes the roots are not real. Sometimes they are imaginary. And this is getting into some very interesting branches of math. So let's start with degree 0 polynomials. An example like y equals 2. That's a constant monomial. We're going to name it. But if we were going to say how many roots it has, well, let's sketch a little graph of it. Okay, what would y equals 2 look like on a graph? Well, I would go up to 2. That's my y-intercept, and there's no slope. So on a graph, it would look like this. A horizontal line, it's constant. And let's check how many times it crosses the x-axis. How many times? No times. There are no real roots if it's a degree 0 polynomial, because it never crosses the x-axis. Okay, so as we move up in our degree, I want you to pay attention to how the number of roots changes, or how it's related to the degree. Okay, so I guess we're done with that one. Degree 1. Like y equals 1/2 x minus 1. Any idea how many times this linear function, degree 1, x to the first power, how many times it will cross the x-axis? Well, let's sketch it. The y-intercept is at -1. I'm going to scale by 2's. And then the slope is 1/2. So up 1 over 2, up 1 over 2, down 1, back 2, because a negative over a negative is still a positive. So if I'm going to connect the dots and make my linear function, how many times does it cross the x-axis? Once. 1 real root. Well, how interesting that when it was a degree 0 polynomial, a constant polynomial function, there were 0 roots. And when it was a degree 1 polynomial function, a linear function, there was 1 root. I wonder if this trend will continue. How about degree 2 polynomials? Well, let's give one example. Y equals x squared minus 1. That's the mother function minus 1, the quadratic mother function minus 1. Okay, so if I'm scaling by 2's, drop it down 1. Okay. So we shifted down 1, out 1, up 1, out 1, up 3. Means how many times does this parabola cross the x-axis? Kablamo, kablamo. There are 2 real roots. But are there always going to be two real roots when we're graphing parabolas? Let's look at a slightly different example. How about y equals x minus 1 squared? Which direction was this parabola shifted? Well, since there's a negative sign inside the parentheses, that indicates a shift in a positive direction to the right 1 unit. I always like to think about what would make 0 in the parentheses. An x value of positive 1 would make 0 in the parentheses. And because 1 minus 1 is 0 and 0 squared is 0, an x value of 1 would give me 0 as my y coordinate. So it would be a right shift, horizontal shift to the right 1 unit. So sometimes our parabolas are sitting exactly on the x-axis, and it appears that there is one real root. But it's not just a single root right there. That is one real double root. So even though it looked like we broke the pattern, it looked like, well, I just showed you a degree 2 quadratic polynomial function that only had one root, it actually does have two roots because that one root is a double root. It bounces and comes back. There's two copies of this factor, x minus 1, which I could write as x minus 1 times x minus 1. And there's two copies of that positive 1 that would make a root. So it's a one real double root at x equals positive 1. So even though it looks like one root, it's actually still two because it's a double root. Double roots bounce and come back. Lola Beans is making this very difficult. But while we're on degree 2, let's just add one more quadratic function to the list, because what if something funky like this happens? Y equals x squared plus 1. How many times will this puppy cross the x-axis? Well, this is a parabola that's smiling because the a value is positive 1, but it was shifted vertically up 1 unit. So how many times does it cross the x-axis? Well, it looks like it doesn't cross at all. There are no real roots. Does that mean there are no roots at all? Well, if they're not real, what could they be? Do you remember last year in Math 2 when we studied imaginary roots? This function actually has two imaginary roots. That is two values that if you plug them in for x, would make 0. And those would be imaginary. They would be, in this case, positive I and negative I, because when you square I, you get negative 1, and negative 1 plus 1 is 0. So if I wanted to factor this into x plus I times x minus I could find some roots. They're just imaginary ones. So we still haven't broken the pattern. Degree 0 polynomials have 0 roots. Degree 1, always 1 root. Lola, get out the way. Degree 2 polynomials can have 2 real roots. Sometimes they have 1 double root. Sometimes they have 2 imaginary roots, but in any event, quadratic functions have 2 roots no matter what. Can you guess where we're headed next? Lola, you gotta move a little bit. Get into our cubics. Will I have room for my cubics? Oops, okay. Okay, so maybe I can do this a little bit smaller so we can fit. Cubic functions, we expect to have 3 roots. This is actually a theorem. It's not just a little pattern we've noticed. It's called the fundamental theorem of algebra, that an n-degree polynomial function has n roots. So for our cubics, it's going to have 3 roots. But what are the nature of those roots? How could they be laid out? Okay, well, one example is that you might have a cubic that looks like this. X times x minus 1 times x plus 2. I know it's cubic, even though it's not written in standard form. I could multiply all of this together, distribute again, and it would be a cubic polynomial because there's an x times an x times an x. There's 3 factors containing x all multiplied together. And the way that that would look is it would have 3 x-intercepts. It would have 3 possible values for x, where you would get 0 if you plug them into this function. And those would occur at -2, positive 1, and 0, because this first x is x minus 0. So a root at 1, a root at 0, a root at -2, and cubic functions look kind of like this. So this is an example of a cubic function that has 3 real roots. It crosses the x-axis 3 times. You can see it, boom. But maybe all 3 of the roots aren't real. How else might we see the roots of a cubic function? What about if it's just the mother function? The cubic mofo is y equals x cubed. Graph that right here. Oops, a little too long. The cubic mother function looks If you cube 0, you get 0. If you cube 1, you get 1. If you cube -1, you get -1. If you cube 2, you get 8. So your cubic function does a little wiggle like so. And it might look like this only has one x-intercept, but really, that is one real triple root at x equals 0, because this is really just x times x times x. And if I asked you what values of x would make this whole thing 0, well, it'd be 0, and then 0 again, and 0 again. So it's actually a triple root at 0. Just like this one is x minus 1 times x minus 1. And if I asked you what values of x would make that 0, well, +1 and +1. That's what roots are, where y equals 0. Okay, how else could cubics be oriented? Maybe you have something like y equals x plus 2 squared times x minus 2. How do I know that's cubic? It's not even written in standard form. Well, it has one factor that's x plus 2, another factor x plus 2 because it was being squared, and then there's an x minus 2. So there's 3 factors all being multiplied. I could do the long and painstaking process of multiplying these all together. But I know that the x times the x times the x would give me an initial term of x cubed, so it's cubic. And what would this one look like? Well, it has a double root at -2, and it has a single root at +2, which means it comes up and bounces at -2, but then comes up through +2 and goes on forever. This is one double root plus one real root. Okay, one double root at x equals -2, and one single root, one real single root at x equals +2. So that's the third way we might see a cubic polynomial oriented on a graph. It may appear that there's just 2 x-intercepts, but this one is a single, just slashes through once. This one is a double root, it bounces there, which indicates there's 2 copies of the factor x plus 2. What value of x would make 0 in these parentheses? -2, -2, and +2. This bounce is the double root. There's one last way we might see cubics oriented on the graph. So for our last example, let's write y equals x squared plus 1 times x minus 1. Okay, again, not written in standard form, but if I were to do the work and multiply this initial x squared by this x, I would have a cubic term. I know what value of x makes this 0, +1. So I know I'm going to have a real root at +1. The value of x that makes this 1, or that makes this factor 0, is imaginary. What kind of thing can you square to get a -1? Well, I is the square root of -1. So this has 2 imaginary roots, and the way that that looks on a graph is like it bounces underneath the x-axis and then comes back up and crosses 1 time. So there's 1 real root at x equals 1, 2 imaginary roots at plus or minus I.